What we're going to look at today is how to do the formulas and names of ionic compounds that contain what are called polyatomic ions. So far, all of the ions that you've dealt with were monoatomic ions. That prefix mono means one. So the ion was made up of one atom that had an overall charge due to the loss or gain of electrons. However, the prefix poly means many. So a polyatomic ion is a group of atoms that are bonded together that have an overall charge and act like a single ion. So some examples of polyatomic ions include sulfate, nitrate, and carbonate. So for example, with sulfate, each individual sulfate ion contains one sulfur and 4 oxygens bonded to it. It acts as a unit, it acts as a single ion, and it has an overall charge of -2. So far, the type of ionic compound that we looked at was a simple binary ionic compound, where you have a metal acting as a cation and a nonmetal acting as the anion. Now these polyatomic ions allow us to have other more complex types of ionic compounds. You could have one that's made up of a metal and a polyatomic ion and a nonmetal, or 2 polyatomic ions together. So one key skill that you need to have is being able to look at a compound and identify whether or not it's ionic. If you have any one of these 4 combinations, that compound you can classify as being ionic. On the back of your periodic table, you're going to find a table that says selected polyatomic ions. These are the polyatomic ions that we're going to use in class. You don't have to have them memorized, but now you need to be careful that you're also checking the back of the periodic table when you are doing a name or a formula to check to see whether or not something is a polyatomic ion. So you're not memorizing, instead you're familiarizing yourself with them. You will familiarize yourself by doing the different practice problems. You can see what's given to you is the formula of each ionic compound and its overall charge, and you're also provided its name as well. So make sure now you're not just using the front of the periodic table, but you're using the back of it. You're using that selected polyatomic ions list. All right, so in order to kind of recognize something as being polyatomic, when you're looking at a formula, it's a lot easier to see. But if you're given a name, what you want to look for is that a lot of polyatomic ions, their names end in "ite" or "ate. What you need to be careful of is a lot of these polyatomic ions also sound like the monoatomic ions as well. So for example, sulfite, sulfate, they're both polyatomic ions, but sulfide is a monoatomic ion. Those 3 things sound the same, but they are different. Nitrite, nitrate, they are polyatomic ions, but then you have nitride, which is nitrogen with a charge of -3. So you really need to pay attention to details. You're checking both the front of the periodic table and the back. All right, so now let's look at naming ionic compounds with polyatomic ions. What you know so far about naming is that if the cation portion is a metal, that metal's name stays the same. If that metal has more than one possible charge, you need to indicate which specific charge it's taking in that compound by writing parentheses with a Roman numeral next to that metal's name. For the anion portion, if it is a single nonmetal, you need to change that nonmetal's ending to "ide." Now, if the cation or the anion is a polyatomic ion, all you have to do is leave that polyatomic ion's name the same. So all of the rules that we talked about still hold, but now if you have a polyatomic ion, you're just going to leave that polyatomic ion's name the same. So let's look at some examples. This first one, CaCO3. This is an ionic compound that's made up of a metal and a polyatomic ion. The metal is calcium, so calcium's name is going to stay the same. Calcium always forms an ion with a charge of +2. So I don't need to put a Roman numeral in parentheses next to calcium's name in the name for this compound. CO3, if I check the back of my periodic table, that is a polyatomic ion. That is called carbonate. So the name of this compound is calcium carbonate. The next one is NH4Cl. This is made up of a polyatomic ion and a nonmetal. That polyatomic ion, if I look on the back of the periodic table, is called ammonium, and the nonmetal is chlorine, so I'm going to change the ending to chloride. So that's going to be ammonium chloride. My last example is a little bit trickier to solve. I have FeOH in parentheses and then a 3. This is a metal and a polyatomic ion. The metal is iron. Iron's name stays the same, but iron has more than one possible charge, so I need to put that Roman numeral in parentheses to indicate which specific charge iron takes in this compound. OH is a polyatomic ion. It's hydroxide, so its name is going to stay the same. So I know I have iron, then in parentheses I need a Roman numeral, and then hydroxide is the name of that polyatomic ion. Hydroxide is a common one that we're going to use in class. Do not confuse that with oxide, which is oxygen with a charge of -2. Hydroxide is also not hydrogen with a charge of +1 or -1. Hydroxide is a polyatomic ion. It's made up of one oxygen, one hydrogen, and it has overall a charge of -1. So now the question is, how do I figure out what needs to go in the parentheses? So I know that I need to come up with that algebraic expression. I don't know iron's charge, so that's where the X is coming from. There's one iron in the formula unit, so I'm going to put 1. Now to look at the anion portion. Hydroxide takes on a charge of -1. There's 3 hydroxides in that formula unit, and then I set that equal to 0. I then go through and solve, and I get that X is equal to 3. So I would plug a Roman numeral of 3 in the parentheses. What I recommend is take that name that you produce, go through the crisscrossing steps to produce a formula, and make sure that formula that you produce matches the initial formula you were asked to solve the name for. All right, so check for understanding. Name the following compound. So Na2SO3. Sodium is a metal. It only has one possible charge. It's always +1. So I know in the name, I'm going to leave sodium's name the same. SO3, when I'm looking on the back of my periodic table, that is a polyatomic ion, so I'm going to leave its name the same. So this compound right here, its name is sodium sulfite. Next one, name the following compound. So I have FePO4. Iron is a metal. It has more than one possible charge. So I know I need that parentheses with the Roman numeral next to it. PO4 is a polyatomic ion. I look on the back of my periodic table. It's called phosphate. I'm going to leave phosphate's name the same. So at this point, I know I have something that looks like this. Now I need to use algebra in order to figure out what that Roman numeral in the parentheses needs to be. I don't know iron's charge. That's where the X is coming from. There's one iron in the formula unit. Each phosphate is going to have an overall charge of -3, and there's one phosphate in that formula unit. So PO4 acts as a single ion. So think of it as being like that it's glued together. Think of it as one whole item. There's only one of them in that formula unit, so that is where the 1 is coming from. I go through and solve for X. I get X is equal to 3. I plug that 3 in the parentheses, and I get iron 3 phosphate. Always check your answer. Make sure that name makes sense. So what I would do is go through, do the crisscrossing, and produce a formula. Make sure that formula matches the initial formula you were given to solve. Now let's look at figuring out the formulas of ionic compounds with polyatomic ions. Everything we've talked about so far still holds. Cation on the left, anion on the right. You're using those charges to figure out what those subscripts should be, and you're reducing down if possible. Now let's look at what we have to do slightly differently when you're dealing with polyatomic ions. So lithium will take on a charge of +1. Phosphate would be PO4, But what I want to do is, so when you have a polyatomic ion, you write the formula of the polyatomic ion that's given to you on the back of the periodic table. When you're at this step where you're setting up the ions, put the formula of the polyatomic ion in parentheses and then put the charge still kind of in that upper right-hand corner. Now what you're going to do is you're going to do the crisscrossing. So that 3 tells me that lithium needs 3 next to it as its subscript in the formula unit. That 1 right there tells me I only need 1 phosphate. If you need only 1 of the polyatomic ion in the formula unit, you drop the parentheses. However, if you need more than 1, keep the parentheses and put the subscript outside of the parentheses kind of in the bottom right-hand corner. Now let me check to see whether or not this formula unit, whether or not it makes sense. So for every 3 lithiums that have a charge of +1, I need 1 phosphate that has a charge of -3. That PO4 is acting as an entire whole unit as a single ion. Don't allow that 4 or those multiple elements that make it up to confuse you. Each individual phosphate is PO4. If that phosphate was in parentheses and there was a subscript outside of it, that subscript outside of the parentheses is what you would use for the ratio when you're trying to figure out whether or not the compound is neutral overall. All right, so now we have calcium nitrite. Calcium takes on a charge of +2. Nitrite is a polyatomic ion. Don't confuse that with nitride. Nitride is that single monoatomic anion form of nitrogen. So nitrite, on the back of the periodic table, its formula is NO2. So I put that formula in parentheses and I put the charge in the upper corner. I now go through and do the crisscrossing. That 1 tells me I need 1 calcium in the formula unit. That 2 tells me I need 2 nitrites in the formula unit. Now that I need more than 1 of that polyatomic ion, I leave it in parentheses and I place the subscript outside of it in the lower right-hand corner. Now based off of that formula unit, that tells me that for every 1 calcium that has a charge of +2, I need 2 nitrites that have a charge of -1. You still can use that final formula unit to see whether or not it makes sense, whether or not that compound would be neutral overall, which it needs to be since it's still an ionic compound. All right, so write the formula of aluminum phosphate. So aluminum takes on a charge of +3. Phosphate is a polyatomic ion. Don't confuse it with phosphide. It's PO4. I put that in parentheses, and then I put that charge in that upper right-hand corner. I go through and do the crisscrossing, and I figure out that I have Al3, PO4 in parentheses, and then a 3 outside of the parentheses. You're still checking to see whether or not the compound can be reduced down. The hard part is making sure you're looking at the subscripts in the formula unit that are giving you the ratio of ions. Those are the subscripts you can change. Those are the subscripts you can possibly reduce. What you can never touch are any of the subscripts that belong to that polyatomic ions formula. Each individual phosphate is PO4. If you were to change that 4, you no longer have phosphate. So I'm looking at those 2 3s right there. Those are the things that I could possibly reduce. So both of them can be divided by 3 and still get whole numbers. So I get AlPO4 as my correct formula. For every 1 aluminum that has a charge of +3, I need 1 phosphate that has a charge of -3. So this is one way to kind of approach this problem and get the correct answer. What I've noticed before is people get really confused with the polyatomic ions and making sure that they reduce everything down correctly. So I'm going to give you an alternate method you could use. You need to figure out what works best for you. So I'm going to do this alternate approach. I write my charges for each ion like that. Those charges, those 3s, are eventually going to be crisscrossed and turned into those subscripts that are giving me the ratio of the ions in that formula unit. So what I can do is, instead of waiting to reduce them down when I get to a formula, I can reduce them at this point. That way I know that I'm not messing with any of the subscripts that belong to the formula of the polyatomic ion. So at this point, I would see those two charges right there. I would then reduce it down to something that looks like this. Aluminum does not have a charge of +1. Phosphate does not have a charge of -3. This is just a trick. It's another way to help you make sure you get a formula that is reduced and is correct. So instead of waiting for them to become subscripts and reduce them at that point, I'm reducing these numbers down while they're still charges. I crisscross, I get AlPO4, I get the correct answer. You need to figure out what works best for you, and that is what you need to kind of use moving forward. Don't allow these multiple elements, the subscripts of the polyatomic ions, to confuse you and not reduce the compound down correctly. Next, write the formula of ammonium sulfate. So ammonium is a common polyatomic ion that we'll use in this class. It's pretty much the only cation polyatomic ion that you'll kind of see. It's NH4, and then in parentheses, and I put a +1. Sulfate is another common polyatomic ion in class. It's SO4, then I put parentheses around it, and then that -2 in that upper corner. I'm now going to go through and do my crisscrossing. That 2 tells me that I need 2 ammoniums in that formula unit, so I'm going to keep the parentheses around ammonium, and I'm going to put a 2 outside of it like that. That 1 tells me I only need 1 sulfate, so I'm going to do SO4, I drop the parentheses. Now I need to be really careful when I'm trying to figure out what that formula unit is. Remember, SO4 is acting as a whole entire unit as a single ion. So technically, my ratio would be for every 2 ammoniums that have a charge of +1, I need 1 sulfate that has a charge of -2. So now that we've done these ionic compounds with polyatomic ions, we've added another level to doing the formulas. If you have a polyatomic ion, when you're setting it up to crisscross, put its formula in parentheses. When you do the crisscrossing, if you need more than 1, you leave the parentheses and put the subscript in the lower right-hand corner. But if you only need 1, you need to drop the parentheses in the formula unit. What I'd like you to do is, in your classwork homework packet, complete numbers 48 through 56. All right, so you can check your answers for 48 through 52. And here are your answers for 53 through 56.